Okay, here we have another circuit that we can use to analyze how Kirchhoff's rules are used, or Kirchhoff, I don't know. You can take your pick on that one. So I've got a circuit with 3 resistors. It might help you to first identify the loops. We can get a loop here. We can call this maybe loop 1, and we can identify this loop here. Maybe call that loop 2. So the junction rule, we want to pick certain junctions. Now you could call this over here a junction if you wanted to, but then you only have one current going in and one current going out, and that only tells you information about this one resistor. So it doesn't make a whole lot of sense to pick this as a junction. You might say, well, this one, it's got several wires or several lines coming off of it, but then this junction is not in any way connected to this 4 ohm resistor up here on the top. So we don't want to pick that junction. So I say that we want to pick this junction because it's connected to all of the resistors. Now sometimes you will run into a problem where you can't connect all the resistors to one junction, and you will have to use several different junction equations. So let's say that current IA is running over this 3 ohm resistor. Current IB is running over the 6 ohm resistor, and IC is running over the 4 ohm resistor. And just based on where the battery is here, it is, at least to me, it makes some initial sense that current IA and IB are going to go into the junction, and current IC is going to go out of the junction. Now remember, if we get any of the currents, like say current B comes out to be negative, that means it actually is in fact going in the opposite direction, which might not make any sense in this one, and I don't think any of these are going to come out to be negative. I think we initially chose correctly. But if you didn't choose correctly, the easy way to fix it is to look for one of your IAs or one of your currents being negative. That means that you chose the direction incorrectly, and you just go back and fix it, and you don't really have to worry from there. So let's get all the currents going into this junction first. So we should get IA plus IB is equal to IC. The currents going into the junction must equal the currents going out of the junction. Okay, so for loop 1 here, notice that loop 1 does not have any batteries in it, and that's okay. That's okay that we don't have any batteries in this one. We'll just still treat it the exact same way. So in one loop, all of the voltage increases must equal the voltage decreases. So if we're saying that it's with this arrow here that I've decided that the current's going into the junction, that means let's just go ahead and pick, or just say that this is going counterclockwise. So in this loop, we're going to come around here, and going across this resistor, we're going to get a decrease of the voltage across this resistor, which will be equivalent to IA times 3, or V equals IR. So the voltage across that resistor is the current times the resistance. And now, going across this junction, we run into this resistor. And this is where we ran into a problem yesterday. I figured out why we didn't get the correct numbers on yesterday's example. That's because if I've decided that this IB is moving to the left here, then that means if I'm going counterclockwise through not counterclockwise, but clockwise, if I'm going clockwise through my loop, then going over this resistor is actually going to be a voltage increase, because IB, we'd be going in the direction against IB. So if we said that it was a decrease, then we would add IB. Well, in this case, we would say that since we're going in the direction opposite IB, that IB would be negative. Oops, it's a B. Times the resistance going over it. We would say that equals 0 because there would be no batteries. Or, I think it's more convenient to just think about if you're going in the direction that you've decided over a resistor, then that's a voltage drop. If you're going opposite to the direction that you've decided for the current, then that's a voltage increase. So we'd have a voltage increase of IB times 6. Okay, so we've got our loop 1. Now to deal with our loop 2 here, I like to start at the battery. So for the battery, we could say that we have an increase of 6 volts. I'm just going to put that on my right side because I've already said this was an increase. So I'm going to get my increases on the right side of my equation and the drops on the left side. So then going across this resistor, across the IB resistor, we get a voltage drop because we're going with the current across the resistor. So I have my equal sign, and we get a voltage drop of IB times 6. And then we continue through the junction, continue along with IC going clockwise with us. So then we go across this 4 ohm resistor, and we're going in the direction we're going the same direction that IC is going. So that's also going to be a voltage drop. So we put it on the same side with my other drops. Let me clean this equation up a little bit. So we get IB times 6 plus IC times 4 equals 6. So there we have 3 equations with 3 unknowns, and we can start solving. So I skipped a couple of steps there because I was working this out, and I just decided to press record here again rather than writing everything out while I'm recording. So let me just talk through. I decided I'm going to use my matrix solving technique. So I need to get all of the variables from each of my 3 equations on one side, so that's why I moved the IC over to the left here, so it equals 0. And then I moved the IB times 6 over to the left side, and I also included a 0 times IC in this middle equation, which I got from this one, also equaling 0. And then for that last equation, there was no IA in it, so I said 0 IA, and then the rest of the stuff. So then I can set up this matrice. And then for my solution matrix, the IA, IB, IC would be equal to the inverse of this matrix, which you can type into your calculator as the matrix to the power of -1 times 0, 0, 6 matrix. And then you can finish solving that from there. So after plugging this into the calculator, we get that IA is equal to 2/3, IB is equal to 1/3, and IC is equal to 1. Notice that none of these are negative, so that means we chose all of our directions correctly at the very beginning.